Hello, everyone. Thank you for watching my lectures on thermodynamics and its applications. I first considered making these videos over a decade ago when I was teaching the graduate course Thermodynamics of Materials at Pennsylvania State University. Today, it has finally moved to the top of my task list. This is partly due to a review article I recently wrote for a special issue dedicated to the memory of Mats Hillert on the 100th anniversary of his birth. Mats sadly passed away in 2022, shortly after the CALPHAD conference held on his home island, Lidingö, in Sweden. As some of you know, I took the graduate course on thermodynamics from Mats at the Royal Institute of Technology, Kungliga Tekniska högskolan, KTH in Swedish. Mats used his teaching compendium in the class, similar to the one showing here. In 1998, after he retired for several years, he published the first edition of his textbook, as shown here. And his second edition was published in 2007, about 10 years later. Dr. Wang and I at Penn State published our textbook in 2016, as shown here. In this series of lectures, I will share what I have learned about thermodynamics and how our research activities have contributed to its understanding, development, and applications. I hope that they are useful to each of you and to the scientific community. If there are enough interest, I can arrange to have live discussing sessions in the future. Thank you. Okay, let us start. Thermodynamics and its applications. My name is Zikui Liu. In Chinese, it is Liu Zikui. As I mentioned, this is my recent article on Gibbs equilibrium and Hillert non-equilibrium thermodynamics in memory of Mats Hillert. In the summary of this article, I wrote, the present author expresses his most sincere gratitude for such an extraordinary opportunity, for without it, the present author might still be stuck in the basin of equilibrium thermodynamics or improperly applying equilibrium thermodynamics to non-equilibrium systems. I hope these lectures will help you to understand the free energy landscape with more basins, saddle points, and apexes between the basins. Lecture 0, Introduction. So what is thermodynamics? In my definition, in my understanding, it is about states of a system. The state can be stable, metastable, or unstable. To understand the states of a system, we have to probe the states through perturbations of the system and measure the responses. So that means we first have to define a system and its surroundings. So what systems can we study? In science or in physical science, we study a substance, a material. We can also study a person, that'd be social science, or psychology, or medicine. We can study planet. We can study black hole as astrophysics, or we can study galaxy. As you know that there are people trying to use thermodynamics to study the universe. However, there's one problem about that one. It's what is the surroundings of the universe? If we cannot define the surroundings, how can we probe its response to perturbations? That remains a question to me. So my journey in learning thermodynamics started when I was an undergrad student in Central Southern University in China, Changsha, Hunan Province. The course was called physical chemistry, so it has physics and chemistry. Second time I learned thermodynamics was at the University of Science and Technology, Beijing, in my master's degree study. The third time was in Stockholm, KTH, learned from Mats Hillert. I joined Penn State in 1999. I taught 2 graduate courses, thermodynamics and computational thermodynamics, among the other courses. In 2016, Dr. Wang and I published this textbook based on my teaching for decades and also our research activities. So our research activities at Penn State have been focusing on thermodynamics. We start with the CALPHAD modeling of thermodynamics. We realized that we needed new tools. So our group have spent quite some efforts to develop tools. We started with SBAY in 2008. And then we have Richard Otis started CALPHAD, and SBAY, then have Brandon Buckland did SBAY. So CALPHAD is for thermodynamic calculations and models. SBAY is for thermodynamic modeling. We realized that we needed more data in addition to experimental data. So we ventured into density functional theory prediction. Our focus was on the free energy, Hermite energy, from the DFT calculations. So we created a tool, DFT-TK, which can predict free energy, Hermite energy, for any given configuration. We found that the prediction for DFT calculations do not agree with experiments. The reason turned out to be DFT calculations for one configuration. But in the measurements, we measure statistical average of many configurations. That's what statistical mechanics does. So we put them together. We created the Zentropy theory. Take the DFT calculation of quantum mechanics and put it into the statistical mechanics framework. We also realized that DFT calculations take a long time. And as everybody knows, artificial intelligence become popular and available to us through the high-performance computing system. So we ventured into the AI by developing machine learning models. We started with PyCyberFun, with its machine learning models for formation energy at 0 Kelvin, developed by Adam Kuryevsky. And we also realized that Zentropy theory is based on the configurations of the system. So it can be used as a foundation model for AI. So we are actively working on that. And because our research activities or projects were paid by the taxpayers' money, so we publish a lot of papers. At the same time, I make our tools and databases open source. It's available on this website, and the GitHub website. To make the community to learn our tools, we also formed the nonprofit Materials Genome Foundation to promote these open source tools. We want to thank all the funding agency from the NSF, National Science Foundation, DOE, DOD to support our activities in the last 25 years. So this paper, also a recent paper, a top review, summarizes our tools, our theories. We call it quantitative predictive theories through integrating quantum, statistical, equilibrium, and non-equilibrium thermodynamics. It has 4 major topics. It Gibbs equilibrium thermodynamics, Hillert non-equilibrium thermodynamics, Zentropy theory for energy landscape, and theory of cross phenomena for flux. To put all our work together, we published a 2-volume books. It's called Zentropy. As I mentioned, Zentropy is our theory developed in our group. Z stands for Zustad summer, and it means the sum of the states, so sum of the configurations put together to predict the entropy of the system. I hope you will enjoy reading them. So we got thermodynamics, we have to use them. So I want to mention about how we have been using thermodynamics in our work. First, we use Zentropy theory to predict the energy landscape. So we can compare the stability, whether it's stable, metastable, or unstable, because we have the energy landscape. And we also realize that the many properties we measure are derivatives of energy. So we can do the first derivative, second derivative, and third derivatives of the energy, get all the properties we measure. If we can predict the properties, then we discover new materials and improve existing materials, or make any system better. Some of you know that I have a TKC theory. Maybe we can use this to make human better. Okay, so let's get started with lecture 1. Thank you for watching.